Hello and welcome to this first video in this series. In this video I'm going to go over the real number system and review some basic arithmetic properties. Real numbers are real in the sense of representing physical measurements of things in the real world. There's actually a whole collection of numbers called imaginary numbers used in some branches of mathematics, but we're going to stick with real numbers for this video series. Within the real numbers, there's rational numbers, which represent fractions and quotients, and then there's irrational numbers, which are any real numbers that are not rational. And so those are numbers like pi, square root of 2, and that kind of number. Rational numbers can be written as either terminating or repeating decimals. So an example of a terminating decimal would be 2/5, which as a decimal is 0.4, so that decimal terminates, it stops. An example of a repeating decimal would be 1/3, because as a decimal number that's 0.333, and the 3's just keep going, so they keep repeating. By contrast, irrational numbers can only be represented as non-terminating, non-repeating decimals. So for example, pi as a decimal is 3.141592, and the numbers keep going with no pattern. And root 2 is 1.41413, and they keep repeating too with no pattern. Within the rational numbers, there are the integers, and we have negative integers, positive integers, and 0. And the positive integers are also called natural numbers. And if we include 0, then these are called the whole numbers. So anytime we're working with numbers, it can be useful to specify which subset of the real numbers we're working with. So if we're working just with whole numbers, with integers, so including negative numbers, maybe we're working with rational numbers, maybe we're also including irrational numbers, so the entire real number set. Next, let's run through the basic arithmetic properties that will need to become second nature to you the further you go in your mathematical journey. We'll start with addition. So if I add two numbers together, it doesn't matter which order I add the numbers. So a plus b is the same as b plus a. So for example, 3 plus 4 is the same as 4 plus 3. It's 7, whichever order I add the two numbers together. If I have three numbers, so a plus b plus c, if I add the a and the b first and then add c, I'll get the same result as if I add the b and the c first and then add the a. So for example, 3 plus 4 plus 2, if I add the 3 and the 4 first, I'll get 7 plus 2. If I do it the other way around and add the 4 plus 2 and then add the 3, I'll get 3 plus 6, and either way I'll get 9. If we have a number and we add 0 to it, then the number doesn't change. And if I have a number and I add the negative of that number, then I'll get 0. Next, multiplication. If I have two numbers that I multiply together, it doesn't matter which order I multiply them. AB is the same as BA. So for example, 3 times 4 It's the same as 4 times 3. It's 12 either way. If I have 3 numbers and I want to multiply them together, if I multiply the first 2 numbers first and then multiply by the third number, I'll get the same as if I multiply the last 2 numbers first and then multiply by the first number. So for example, 3 times 4 and then times 2, so that'll be 12 times 2, so 24. It's the same as if I do 4 times 2 first, which is 8, and then 3 times 8 is 24. So same answer either way. If I have a number and I multiply it by 1, then the number will stay the same. And if I have a number and I multiply by 1 over that number, and 1 over the number is called the reciprocal, then I'll get the number 1. Next, if we multiply a times b plus c, then that's the same as a times b plus a times c. So for example, if I have 3 times 4 plus 2, then one way I could calculate this is add the 4 and the 2 to get 6 and multiply by 3. So 3 times 6 is 18. Well, the other way I could calculate it is to use this result up here, and I could do 3 times 4 and add 3 times 2. So 3 times 4 would be 12, and then 3 times 2 is 6, and then 12 plus 6 is 18. So I get the same answer either way. And this can be useful when we're solving more complicated equations. Sometimes it's easier to calculate using this method. Sometimes it's easier to calculate using this second method. Building from this last property, if I now have a plus b times c plus d, we can expand this into 4 what are called partial products. So the first partial product taken from the first 2 pieces, so the a and the c, would be ac. And the next 2 numbers that I'm going to multiply are the outer 2 numbers, so a and d. And then the next 2 numbers I'll multiply are going to be the inner numbers, so b and c. And then the last 2 are b and d. So we had the first 2, and then the outer numbers, and then the inner numbers, and then the last 2 numbers. So that spells out the acronym FOIL. So this is typically known as FOIL. And so for example, if I have 3 plus 4 times 2 plus 1, just as in the previous example, I had 2 different ways of calculating. I'll do 2 different ways for this example as well. So I could do this, 3 plus 4 is 7, and then 2 plus 1 is 3, and 7 times 3 is 21. Or I could use FOIL, and I'll do the first 2 numbers, so the 3 and the 2. And then next one is the outer numbers, so 3 and the 1. The next partial product is going to be the inner numbers, so the 4 and the 2. And then the final one is the last numbers, so the 4 and the 1. So So 3 times 2 is 6, 3 times 1 is 3, 4 times 2 is 8, and 4 times 1 is 4, 6 and 3 is 9, plus 8 is 17, plus 4 is 21. So I get the same answer either way. And again, just as in the previous example, sometimes in more complicated expressions, it's easier to work with this calculation method, and sometimes it's easier to expand it and use this calculation method. And finally, I'm going to finish up thinking about equations and solving equations. And I'm going to use this property here. If I have an equation a equals b, and I want to solve that equation, as long as I do the same thing to both sides of the equation, then that can be a way of simplifying the equation to solve it. So, for example, I can add the same number to both sides of the equation. So a plus c is the same as b plus c, or I can multiply both sides of the equation by the same number. So a times c is the same as b times c. So for example, if I had the equation 2x plus 3 equals 9, and I want to solve this equation for x, so I want to isolate x on one side of the equation and just have numbers that I can evaluate on the other side of the equation. So the first thing I want to do is I want to move that 3 from the left-hand side of the equation and move it over to the other side. So one way to do that is to subtract 3 from both sides of the equation. So I'm using this idea here. So I'll have 2x plus 3 minus 3 is equal to 9 minus 3. And now plus 3 minus 3 is 0, and I'm left with 2x on the left-hand side of the equation, and I'll have 6 on the other side. Next, we have to do something about the 2 here. So I need to think of a number that I can multiply by 2 to get 1, so that I'll have 1 times x, which is equal to x. So if we think back to one of the properties from earlier, if I multiply 2 by the reciprocal of 2, which is a half, then I'll end up with 1 times x, and I'll have x on the left-hand side. And then I have to do the same thing to the other side of the equation. So multiply by a half. And so now I've got 1 times 2 is 1, and 1 times x is just x. And then on the right-hand side of the equation, I've got a half times 6, which is 3. And there's my answer. Anytime I solve an equation like this, it's always a good idea to do a check at the end that your answer does actually solve the equation that you were trying to solve. So to do that, I'll plug in the answer that I got into my original equation. So 2 times 3, and then we're adding 3, and then we should be getting 9. 2 times 3 is 6, and sure enough, 6 plus 3 equals 9. So that's a good check that I've not made any mistakes during my series of manipulations here. So that's all for this video. In the next video, I'll look at representing numbers as points along a number line.